Have you ever wondered why light can fall into a black hole without being pulled by force in the usual sense? Here's the twist. Black holes have a hidden light ring where photons can orbit, but only in a way that's catastrophically unstable. A tiny nudge sends the photon either escaping to infinity or plunging inward, and the divergence between nearby photon paths grows so fast, it's described by a Lyapunov exponent. So the misconception to kill right away is this: if light can orbit, it must be stable. It's not. The photon sphere is more like a spinning razor blade than a stable racetrack. This matters because the chaotic instability leaves fingerprints in what we can observe: the black hole's shadow edge, the timing of quasi-normal ringing, and the subtle patterns behind gravitational lensing. The open loop is simple. How can geometry create both an orbit and a chaos engine at the same time? And what does Lyapunov divergence actually mean for something as fast and seemingly rule-bound as light? Before we dive into the math, picture what physicists expected. In Newtonian gravity, circular orbits can be stable or unstable depending on how force changes with radius. In general relativity, the force is geometry. Matter tells space-time how to curve, and curved space-time tells everything how to move. Decades ago, theorists studied photon motion in Schwarzschild spacetime, the simplest model of a non-rotating black hole. The surprising prediction was that null geodesics, paths light follows, include a circular orbit at a specific radius. But possible didn't mean safe. The question was whether the orbit would act like a comfortable circle where small perturbations die out, or like an unstable equilibrium where they explode. Now the deep dive. Imagine a photon launched near the critical circular orbit. The photon sphere sits at a radius of r equals 3 gm c squared for a Schwarzschild black hole, where m is the mass. At that radius, the effective potential governing radial motion has a peak. The peak is the key. For a stable orbit, the potential would have a valley. Small displacements produce a restoring force. For the photon sphere, it's a hilltop. A photon exactly at the top can orbit forever in idealized symmetry, but the slightest radial drift moves it down either side of the hill. Here's the mechanism in more intuitive terms. Take two nearly identical light rays with slightly different impact parameters. Think of them as shooting through nearby lanes in the black hole's gravitational funnel. Even though both rays obey the same geodesic equations, the geometry amplifies the difference. One ray finds itself effectively pushed toward the direction that reduces its turning point, so it never re-emerges. It crosses the event horizon. The other ray's turning point shifts outward just enough to allow it to scatter back to distant observers. The system acts like a selection gate with an exponentially growing sensitivity to initial conditions. This is where Lyapunov divergence enters. In dynamical systems, if you track a tiny perturbation delta between two trajectories, chaotic systems make it grow approximately like delta on Trouble delta e's to the power of lambda t, where lambda is the Lyapunov exponent. For the photon sphere, lambda can be related to the curvature of that effective potential hill. Steeper peaks mean faster divergence. Chaos here isn't randomness injected from outside. It's deterministic instability intrinsic to space-time geometry. The black hole doesn't need to shake the photon. Geometry alone ensures that small differences in initial direction translate into dramatically different outcomes. If you want a more visual analogy, picture a marble balance at the very top of a perfectly smooth hill. The marble can sit there in principle, but any imperfection, air currents, microscopic bumps will send it either left or right. Photons are like the marble, except they don't fall under a classical potential. They follow curved space-time's null paths. Two marbles starting nearly together separate exponentially, and the separation time sets the scale for when the photon's fate becomes effectively irreversible. In black hole scattering, the number of whirls a photon executes near the sphere before escaping or falling is controlled by how close its constants of motion are to the critical values. Because the divergence is exponential, the dwell time near the photon sphere, and thus the pattern of echoes in the outgoing radiation, follows a logarithmic relation with that closeness. That brings us to discovery and observation in practice. Theoretical calculations of photon sphere dynamics predicted that strong gravitational lensing near the photon sphere would produce multiple images, including relativistic images corresponding to photons that loop around the black hole one or more times before reaching us. The instability dictates that photons that orbit more times require initial conditions tuned closer to the critical impact parameter. Since trajectories diverge exponentially, each additional loop corresponds to a much tighter window of initial parameters, which is why the images rapidly decrease in brightness and cluster near the edge of the shadow. But the broader implications are bigger than optical tricks. The Lyapunov instability ties directly to the stability of the black hole's ring down. When a perturbed black hole relaxes back to equilibrium, the emitted gravitational waves and electromagnetic signals can show characteristic frequencies and decay rates. The photon sphere governs how null disturbances get trapped temporarily, and the instability rate influences how quickly those trapped modes leak away. In other words, the same chaos engine that separates photon paths also shapes the temporal fingerprint encoded in observed signals. For modern astronomy, this means the black hole's mass and spin can be constrained by how the shadow's boundary behaves and how radiation decays in time. And in the deeper physics sense, it provides a rare meeting point between general relativity and dynamical systems. Lyapunov exponents are not just a mathematical curiosity. They quantify a kind of information scrambling in classical terms. Even though quantum chaos and horizon thermodynamics involve additional layers, the photon sphere offers a classical laboratory for sensitivity to initial conditions, an intuition that later links to ideas like scrambling and chaos bounds. You can think of it as space-time itself acting as a non-linear system that magnifies microscopic differences into macroscopic observational consequences. So, what have we learned? The photon sphere is not a stable halo, it's an unstable light orbit at an effective potential maximum. Any tiny perturbation pushes photons away from the circular geodesic, sending them either inward to doom or outward to freedom. The divergence of nearby trajectories grows exponentially, captured by a Lyapunov exponent tied to the geometry of that potential peak. This instability doesn't just make the math interesting, it imprints itself on strong lensing patterns, shadow features, and the time domain behavior of radiation near black holes. When you next see a black hole shadow, an apparently smooth, dark disk, remember there's a razor-thin border where light behaves like a chaotic billiard ball, spinning around an unstable ring whose instability is measured by exponential divergence. Space can be calm and still be unstable. Geometry can be deterministic and yet amplify difference faster than intuition allows. If you want more science that turns cosmic mysteries into crisp mechanisms, subscribe for more.